Welcome back to another chemistry tutorial with me, Miss T, a qualified teacher, Oxford University graduate, and your friendly neighborhood online tutor. For this video, we'll be going over molar gas volumes, starting with some definitions, worked examples, and then some practice questions. So it's Avogadro again. This time we're not talking about his constant, we're talking about his law as it applies to gases. So Avogadro's law states that equal volumes of all gases at the same temperature and pressure have the same number of molecules. Or in other words, a given volume of gas will always have the same number of moles if temperature and pressure are constant. So whether you have oxygen, carbon dioxide, hydrogen, helium, if it's the same volume, it will be the same number of moles of each of those gases. So we just mentioned that those things are true when temperature and pressure are constant. And there are a couple of common temperatures and pressures used at A level and IB. So the first is called STP, or standard temperature and pressure, which is 273 Kelvin and 100 kilopascals. The second common temperature and pressure combination is room temperature and pressure, or a IB, that's called standard ambient temperature and pressure, which is 298 Kelvin and 100 kilopascals. So again, the volume that 1 mole of gas can occupy will be the same if it's at a particular temperature and pressure. So at standard temperature and pressure, 1 mole of gas will occupy a volume of 22.4 decimeters cubed. Or in the IB data booklet, that's given as 22.7 decimeters cubed. At room temperature and pressure, or standard ambient temperature and pressure, 1 mole of any gas will occupy a volume of 24 decimeters cubed. So we call those the molar gas volumes. So at STP, the molar gas volume is 22.4 decimeters cubed per mole. And at RTP, or SATP, the molar gas volume is 24 decimeters cubed per mole. 1 mole of a gas will occupy that particular volume. So with that, we can now calculate the number of moles based on the volume and the molar gas volume. So at the top, V is the volume of gas in decimeters cubed. Vm is the molar gas volume, which at STP is 22.4 and at RTP is 24, and then N is the number. So for our first worked example, calculate the amount of hydrogen in 480 centimeters cubed at 298 Kelvin and 100 kilopascals. In chemistry, when we use the word amount, we mean moles, and moles equal volume divided by the molar gas volume. In this case, as we're dealing with room temperature and pressure, the molar gas volume is 24 decimeters cubed per mole. Now, as the volume in the question is in centimeters cubed, we've got two options. We can either convert our molar gas volume into centimeters cubed per mole by multiplying 24 by 1000, and then moles equals 480 divided by 24,000, which gives us 0.02 moles. Our second option is to convert our volume into decimeters cubed by dividing it by 1000. And so we get 0.480 divided by 24 decimeters cubed per mole to give us the same answer of 0.02 moles. For our second worked example, we need to think about Avogadro's law using the balance symbol equation and the stoichiometric relationship between the reactants and the products. So first, just looking at the balanced equation, how many moles of ammonia can be made from each mole of nitrogen? Well, it's a ratio of 1 nitrogen to 2 ammonias, so 2 moles of ammonia can be made from every 1 mole of nitrogen. And so with that in mind and utilizing Avogadro's law, if we start with 150 decimeters cubed of nitrogen, what volume of ammonia can be produced, assuming the yield is 100%? Well, if 1 mole of nitrogen makes 2 moles of ammonia, 150 decimeters cubed of nitrogen is going to produce 300 decimeters cubed of ammonia, as 1 mole of any gas is going to occupy the same volume at a given temperature and pressure. For our final worked example, at 298 Kelvin and 100 kilopascals, what is the volume in decimeters cubed occupied by 4.0 grams of hydrogen? Well, first we need to calculate our moles of hydrogen. When in doubt, find the moles as mass over mR to give us 2.0 moles of hydrogen. Now we can calculate our volume as moles multiplied by the molar gas volume, in this case 24 decimeters cubed, as we are at room temperature and pressure. And that gives us a value of 48 decimeters cubed. Okay, your turn to have a go at these questions. All of the relative atomic mass values that you need are over on the right-hand side. Pause the video now and press play when you're ready with your answers. So question number 1, we are calculating moles. Moles equals volume divided by the molar gas volume. So for our first example, 480 divided by 24, which gives us 20 moles. And for our second one, again, we can either convert our molar gas volume into centimeters cubed by multiplying by 1,000, or convert our original volume to decimeters cubed by dividing by 1,000. Either way, we get an answer of 0.05 moles. For our next question, what is the volume occupied by 3.2 grams of methane at standard temperature and pressure? We're given the mass, so first we need to calculate the moles as mass over mR, which gives us 0.2 moles of methane. Then volume equals moles multiplied by the molar gas volume. We're at standard temperature and pressure, so that's 22.4 or 22.7 if you're in IB, which gives us an answer of 4.48 decimeters cubed. And then we'll give our answer to 2 significant figures, as that's what we've got in the question, 4.5 decimeters cubed. So for our next question, we are using Avogadro's law that equal volumes of all gases at the same temperature and pressure have the same number of molecules. So the ratio between methane and oxygen is 1 to 2. So for every 1 mole of methane, we need 2 moles of O2. So if we're burning 1 decimeter cubed of methane, we need that to react with 2 decimeters cubed of O2. The ratio between methane and carbon dioxide is 1 to 1. So if we burn 1 decimeter cubed of methane, we'll produce 1 decimeter cubed of carbon dioxide. And our final question, using stoichiometric relationships. First, we need to calculate our moles of magnesium carbonate as mass over mR to give 0.0174 moles. Our ratio between magnesium carbonate and carbon dioxide is 1 to 1, so we'll have the same number of moles of carbon dioxide. Multiply that value by the molar gas volume at standard ambient temperature and pressure, which is 24 decimeters cubed per mole, to give us a final volume of 0.419 decimeters cubed. So how did you do? Leave a comment with how you found this lesson, anything that you want explained further, or any suggestions for future videos. See you next time for another Miss T chemistry tutorial. Bye.